Welcome to today's webcast. Ditch upgrade results in energy savings at North Cary Water Reclamation Facility. A special thank you to today's sponsor, Veolia. And we are excited to be joined by today's presenters, Ashley Waples and Pia Prowaska. Ashley has been with Veolia Water Technologies in Cary, North Carolina for 16 years. She has worked across multiple product lines as pilot engineer, process engineer, application engineer, and now a product manager for Veolia's Ditch and PMT Technologies. Pia has been with Veolia Water Technologies for 30 years. She moved from Denmark to the U.S. in 2009, where she has worked for Veolia Water Technologies in Cary, North Carolina for the last 14 years. She has worked across multiple product lines as a R&D engineer and process engineer and is now a senior process engineer for Veolia's activated sludge and fixed film technologies. And now, Ashley, I will turn it over to you.
Great. All right, thanks everyone. Thanks WEF for hosting, and thanks all for joining us. Today, as we introduced, we'll be discussing a ditch upgrade and some energy savings that we're seeing at our North Cary Water Recreation Facility right across the street from our office in Cary, North Carolina. As an overview, we'll talk a little bit about Veolia's ditch technologies. This is an activated sludge process, essentially, with some phasing. The key benefits for wastewater treatment plants, and then we'll talk about our upgrade reference and some advanced online controls. So Veolia Water Technologies installations, we have been working on the ditch installations in the United States for over 30 years now. We have over 100 installations in our biodinitro and biodinifo AE dinitro configurations. The majority of these fall in the 1 to 5 million gallon per day category. But we have some quite a bit larger, North Cary being one of our largest installations, and also quite a few under the 1 MGD size. About half of these are biodinitro process, which is our phased activated sludge process, and we'll chat a little bit more about that here in just a minute. So here's a configuration of our biodinitro process. As you can see, it looks like 2 oxidation ditches, but we operate these in series. So they are flowing into one, going around, receiving aeration, and then flowing into the next phase where they would see an anoxic or another aerobic mode. And the real benefits of this process is that we have full capability to operate either ditch in anoxic or aerobic mode with rotors as aeration, or with fine bubble diffused air, or even jet aeration. And then we use typically some large banana prop propeller type mixers to help keep the flow moving around the ditch, as well as to allow us to turn off that aeration and have some energy savings. So with this configuration, we don't have any internal mixed liquor recycle pumping. All of the flow is just going back and forth between the 2 ditches. It's controlled at the front. Oh, here's my cursor. You can see we have a distributor where we're able to distribute to one ditch or the other. And then both the level in the ditches as well as the flow exiting the ditch is controlled by a weir in the back. Across here, you can see this is a rotor configuration, and then here are our mixers. So we don't have a separation of, so we have a separation of mixing and aeration in each tank with essentially unlimited aeration turn down. The next slide will show that a little bit clearer. So this offers a huge degree of operational flexibility when compared to a traditional activated sludge process. and that we don't have a set volume or a set hydraulic retention time in each zone. We can essentially change the amount of time that we operate in either anoxic or aerobic mode, which allows us to meet a total nitrogen limit of less than 4, maybe 5 total nitrogen without having secondary anoxic zones. So here's a little graph representing that phasing based on some time-based control. At the top, you can kind of see how we would have nitrification versus nitrification and denitrification mode occurring. Again, we would come into the denitrification mode and then go to the nitrification mode. And then we can control the duration, whether it be fully nitrifying or adding more and more denitrification period up to about 50% denitrification, which can save us a lot of energy. Think about nighttime when we have lower loads coming in. Instead of constantly operating those more energy guzzling rotors or blowers, we're able to turn those off more and operate the mixers only for a longer period of time and still meet our effluent requirements. Moving on, that's exactly what we're doing here at the North Cary Water Reclamation Facility. Here's an aerial shot of the plant. This is actually 3 trains. So we have 3 biodenitro systems. So the nomenclature here is a biodenitro would just be the 2 ditches in series. When we call it a biodenitro, that just means that there's upfront anaerobic selectors. So we're actually seeing some biological phosphorus removal. So we have the 3 trains here. Each of them has been upgraded to diffused air from rotors to acquire some energy savings, along with some updated wet chemistry control. And then they're each followed with a clarifier. And here is a little bit more on that. So the primary goal of this project, it was an existing, or it is an existing plant that had a 12 MGD capacity. They wanted to increase that aeration capacity to 15 MGD without adding any additional volume. So what we did here is we converted everything from rotors to diffused air, and then added some online control strategy with wet chemistry monitoring that Pia will talk a little bit more about shortly, in order to remove at least as much nutrients and treat more flow in the same volumes. So our goals are to remove to achieve less than 3 milligram per liter of total nitrogen, less than 1 milligram per liter of total phosphorus, and then less than 0.5 milligram per liter of ammonia. This is a plant that uses some of the flow for reclamation. So some of that flow that's treated is used for irrigation in communities nearby. So one of the secondary goals of the project is to operate without any external carbon. And that right now is still working. Good. Okay, so what we did, we came in and each train went through and had the rotors replaced with diffused air to increase the aeration capacity. That was an easy way. You were able to adjust the amount of air a little bit more uniquely, as opposed to just adding an additional rotor to each ditch. And then a new blower station was installed. This was a centrifugal blower station, and we'll talk a little bit more about that next. The existing mixers were able to remain in place for mixing during anoxic, as well as to help flow move around the ditch. And then we installed online ammonia and nitrate analyzers with wet chemistry, and then upgraded the control for time-based control, from time-based control to real-time PLC online control. Right now, 2 of those 3 trains are in operation. They're only currently seeing about 7 million gallons per day. So the 3rd train will be ready to go online as soon as some other capital expenditures happen to increase that full flow for the full 15 million gallons per day. But already we're seeing a reduction of about 6% of the overall energy to the plant, which would be able to be increased more if we weren't underloaded and or using centrifugal blowers. So right now, those centrifugal blowers are not the most efficient type of blower when you're comparing to either a turbo blower or a screw compressor blower. And they're also oversized right now and blowing off a good bit of the excess flow at nighttime. The average effluent values are seen below. So this plant is operating really well. As you can see, we were already below 2 milligram per liter total nitrogen before the upgrade. And now since the upgrade, we're seeing about 1.8 milligram per liter total nitrogen. And again, slightly reducing the total phosphorus out the back as well. And just to give an overall idea of what that 6% energy savings looks like, it doesn't seem like a big number, but for a plant this size, that equates to somewhere in the range of $60,000 per year. If we're using about 10 cents per kilowatt hour. So we're also able to have just a deeper understanding of how the biological process works through the online measurement of our nutrients with the online controls. So with that, I will hand over a little bit more to Pia.
Okay. So I was also the engineer that worked with the North Cary plant, and what we used there was a PLC-based online control. And when you look at PLCs, you can't make too advanced control algorithm programmed in the PLC. So that's why Veolia Water the last 30 years have developed now we're on cloud-based online control system, which we are calling the HubGrade performance and HubGrade plant performance. The first plant or the first installation happened more than 30 years ago, and that was something I worked with very intensely in Denmark. Since then, we have more than 100 reference plants, mainly in Europe, but we do have a couple of plants here in the United States as well. But if you want to, as I said, if you want to have more advanced control, you have much more complex algorithm. And as you said, that has to be done more in a computer than in the PLC. So also, why do we want advanced optimization? So what I'm seeing here in the United States very often is that we go in and we focus a lot of reducing the operation cost. We look at DO control, ammonia-based DO control, where the ammonia concentration in the reactors will be the one that will decide what DO set points that we are operating at. We will use a nitrate probe in a post-anoxic zone to decide how much and when to dose external carbon. And what we will see there is a reduction of the energy and the chemical use of chemicals. And that is fine, but there is a lot more to gain by implementing online control, and especially when it's more advanced. And so what you can do is you can increase your hydraulic capacity by reducing overflow or bypass in the wastewater treatment plant and increasing the flow through the existing plant. Also, what I don't see happen a lot here in the United States is increasing the biological capacity. So basically what we do is that when you have a given volume, or like a plant like North Cary, you have a certain volume. It is designed for a load of 12 million gallons per day, but you want to increase that load. And by implementing more advanced control, you can use this volume in the most optimal way. So you always adapt the processes that's in there at the excuse me, at the most optimal way. The other thing that we also look at, which is also fairly new, is that we also look at the sewage system. So by implementing online control of the whole sewage system, it is much you can obtain a reduction of the combined sewer overflow, and you can save capex on the extension of the retention basin volumes. A little bit more subtle reasons to implement advanced optimization is that that, for instance, the operators, that which Ashley also mentioned, they suddenly have a much more close knowledge of what is actually happening in the wastewater treatment plant. How is the ammonia concentrations going on? What is the nitrate concentration? And that will ensure that they are much more, they have a much higher knowledge of the process. So what typical savings and what goals can we normally meet with implementing these advanced online control systems? As we're all aware is that we can obtain less energy consumptions. The aeration, the amount of energy that's used on a wastewater treatment plant, the aeration is far the largest part of that. And we obtain at least 10 to 30% reduction of the aeration by implementing these systems. We also sometimes we will have VFDs on our mixing. So when we have low nitrate concentrations, we will actually slow down our mixers and save some money there. And then there's also some savings on energy on controlling the internal pumping based on the nitrate levels that you are seeing in your reactors. The other thing is less chemical dosage. And in regard to pre-precipitations, there's two reasons why we can reduce that. We can actually implement biological pee removal in existing plants that do not or are not born with anaerobic reactors up front. Or we will dose and then the chemical addition can be controlled also by phosphate analyzers, so you're not overdosing your chemicals to meet your effluent requirements for the phosphor. Especially, and then of course, if you have external need for an external carbon to meet your total nitrogen requirements, you will also, both because you are actually doing a process optimization in your main processes by controlling the phases, the length of the oxic phases and the length of the anoxic phases, then your overall effluent has a lower amount of nitrate, which means that when you get to the post-anoxic zones, you have less requirements for external carbon addition. So that overall will also lead to a less chemical sludge production. What I find most interesting is that you can actually intensify your wastewater treatment plant. As I said, you can get a much higher flow through the plant during high peak load situations. We very often see that we can get about 50 to 100% higher flow rates through that without any issues with the secondary clarifiers. we can use that either, as I said, to get the higher flow, or if we build a new wastewater treatment plant, we can look at the design of the secondary clarifiers and potentially decrease the amount of clarifiers that is needed in this project. We did that on a plant in Warsaw, where we reduced the amount of secondary clarifiers and saved on the capex there. The other thing is, as I mentioned before, is that these advanced online control system, they allow you to actually treat 10 to 40% more load. As you heard at the North Cary plant, we increased the actual load that this plant can handle from 12 mgd to 15 mgd. And then, of course, when you implement these online control systems, you will get a better effluent quality. We see normally a improvement in the total nitrogen in the effluent between 20 to 50%. And on total phosphorus, we get something between up in the range of 50%. In regard to BUD, CUD, and TSS, we don't necessarily see such a big improvement there, because on a normal BNR plant, these numbers are all already relatively low. Of course, the better effluent quality also depends on how well this plant has been operating before. So like a plant of North Cary, where there was 24/7 operator on site, and they were very aware of their effluent, and they were always following the process, as you can see, and they were already getting a total nitrogen that was less than 2. The improvement of the effluent quality, you don't see. I mean, it's difficult to get much better than 2 anyway. So of course, depending on how it's already operated, the savings will be, the improvement will be more or less. A more subtle or another thing that is now getting more and more interesting in our world and nowadays is that we all are going to look at the carbon footprint of these wastewater treatment plants. They have a rather large footprint as of now. One of the reasons is that these plants, if they're not properly controlled, they will actually have a lot of laughing gas, N2O, coming out of the process. And by controlling your biological process, and you are actually able to reduce this number by up to 50 to 90%, and decrease the overall CO2 footprint of your wastewater treatment plant by 10 to 30%, which is quite a lot. As of now, we have about 4 plants in Denmark that are operated with this module, and is showing very promising results. So that is definitely something that we will see more and more of in the future, that we have to look at these points of carbon footprints. So what is a big difference when you have like a more traditional control, where everything is controlled just by the PLC, and then when you have introduced these advanced optimization methods? So when you have a traditional wastewater treatment plant that is controlled by a PLC, you have your SCADA system, and you put in some certain set points in there, and those set points are set fairly conservative, so you can kind of meet both high loads and low loads, and you can change those set points if you have plant operators, as for instance in North Cary, that manually went in and changed these set points. They would keep changing the set points depending on the effluent quality of the plant. So you can do some optimization in that PLC, and get closer to the ideal process control. But in order to kind of get it really good, you need to have a machine, because otherwise the plant operator wouldn't do anything else. So when you have an online process control, what we do here is that every 5 minutes, the PLC will actually send the process parameter up in the cloud and we will look at what are the process conditions here and what effluent and what is the conditions in the reactor. And then based on these algorithms and which modules that is in play that we're using at this wastewater treatment plant, the cloud or the algorithm will send new set points down to the wastewater treatment plant every 5 minutes and adjust the DO every 5 minutes. DO set points will adjust the phasing, or at least take a look if they need to change anything. And so that means that all the set points and is constantly following the diurnal load variation that you see on the plant, or the weekly load, or also the yearly load variations. And you will obtain, as I said, you will use all your volume in the most optimal way. So when we talk about the upgrade performance plant, our advanced online control product, we have, I don't know, 20 different modules that you can add to this, depending on what it is you actually want to obtain here. When we first implemented this on our first wastewater treatment plant, the module that we call the DO and nitrogen removal module, that's the first module that we used and implemented. And that's basically the backbone when you look at process optimizations in the wastewater treatment plant. And why would you implement that? That is in order to ensure that the plant is able to comply with the effluent requirements. So it could be a plant that has issues with their effluent quality and can't meet it, or it could be, as North Cary, a plant that are seeing a big growth in their population and needs to be able to treat more wastewater. And then instead of going out and invest in new volume, they can optimize the process in the existing volume. And as a sidekick, you get a reduced energy use, and also you get reduced carbon footprint emissions. And how do we do that? What is the idea? So basically, when you have a wastewater treatment plant, you will have a set volume of aeration. You will have a set volume for nitrogen removal and anoxic volume. And that volume is kind of set when you do the design, and it's kind of set there. And you very often don't vary that volume, but by controlling the aeration, for instance, if you have a BNR plant where you have multiple aeration reactors in series, you can take some of those aeration reactors, turn the air off in them, and turn them into anoxic zones and get some more denitrification and avoid over aeration. So in order to improve the nitrogen removal, there's two things that's important: that we don't over-aerate, which we very often do during low load situation, during the evening or during the weekend, or whenever there is a low load situation. The other thing is that in order to improve the nitrogen removal is how to utilize the incoming BOD that is in your wastewater in the best given way, and not burn it off on aeration when it could be used for denitrification. So that's basically the idea behind this this module. And we use two patented optimization control. We do regulation of the DO set points, which is basically what you see here that is done on multiple plants here in the United States. But also, as I said, we regulate the nitrogen and denitrification. So we switch phases, basically. When the ammonia concentration reached a certain concentration, then we switch to anoxic conditions instead of just keep over-aerating and wasting BOD from the influent or excuse me, or can be used for simultaneous denitrification if the aeration zone is the back end of the plant. You can see the graph on the lower end of the slide, and the blue line is the nitrate concentration and the black line is the ammonia concentration, and the left side is before integrating the hub-grade performance plant and the DO and the nitrogen removal module on this plant. You can see the nitrate is high, and you can see the ammonia is relatively low. It's like a 0.5 constantly. So by implementing anoxic zone, the anoxic time in this plant, or increasing the if you have a biodinitro, it's easy to change the ratio between nitrification and denitrification. So you can increase the time for denitrification, and you can see that that you will have that the ammonia concentration will go up, but you can also see there's a huge reduction in the nitrate. And the overall result here will be a lower total nitrogen number, and also a huge, significant savings on the energy, because you don't over-rate, you don't use your aeration equipment constantly here. One of the other modules that is very popular right now is, as I mentioned before, the reduction, the module that would ensure the lowest emission of laughing gas. And what it does there, so it goes in and it measures the laughing gas with a sensor in the wastewater treatment plants. And basically, it aborts the aeration and ensure that you have denitrification, and that will ensure the lowest emission of the laughing gas at the plant. This is very efficient, and the plants, as I said, we have about 4 reference plants as of now, and we have seen a reduction about 30% of the overall carbon footprint coming out of these plants. Another module that is very interesting and will ensure that you can actually have biological pee removal in a system that was not born with anaerobic bio-pee selectors up front. We have used this on numerous plants here with very good results. It doesn't have to be any special plant configuration. So basically what we do is we enhance the biological pee removal, and how it's done is that we identify times where we have a low load coming into the plant, where there's basically time or volume available to actually turn that into an anaerobic condition. And by doing that, we actually achieve biological pee removal throughout the plant, and reduce the amount of chemicals that is needed, and also reduce the amount of chemical sludge produced in the plant. I think we have about 10 to 15 reference plants on this one, and it's very interesting for sure. So, as I said, we have a couple of reference plants. We have the Helsingør wastewater treatment plant, which is a wastewater treatment plant of about 75,000 PE. There we saw a reduction of 80% of the chemical used before. And at Nosido plant, which is a 1.25 million PE plant, we saw a 70% reduction of the chemical use. And at plant in the Netherlands, also we saw a 20% reduction. And all this, we are doing that without any bio-pee tanks. So it's highly efficient. And is a way to obtain biological pee removal, again, without having to introduce any anaerobic tanks on existing plants. we have other reference plant. That we have this plant here in the island, and we had the Upgrade Performance plant running there for 5 months, and we saw at this plant an overall energy savings of about 35,000 euro. The specific energy consumptions was reduced with up to 45%, and the daily average consumptions was reduced with 32%. So again, if you look at the graphs here, what we did was that we increased the amount of anoxic time that was in the system. And if you look at this second graph, you can see the black line, yeah, if you look at the second graph, the black line is the nitrate concentration in the last zone. This is a BNR plant with multiple aeration zones, and we reduce we controlled the aeration in those aeration zones. We turned them on and off and introduced anoxic volume there. And by doing that, we decreased the amount of nitrate coming out of this plant significantly. But as you can see in the blue line is that the ammonia concentration did go up. At this plant, there was not a specific ammonia concentration limit, so we were allowed to do that. Of course, if you have plants where you have to keep an ammonia concentration less than 1 or 0.5 even, you don't have the same ability to turn off the air as much, because you have to first and foremost ensure that you're meeting the ammonia effluent concentration, and after that you can look at your total nitrogen. But the result here, as you can see, is that the blower station, the kilowatt of the blower consumed in the blower station, went down significant with a huge reduction in the energy consumption. Another case study. This is one of our definitely one of our reference plants. This is a wastewater treatment plant in Kolding, in Denmark, and it's this about 90,000 person equivalent size plant. There they have basically all the modules that we have in the Upgrade Performance plant system. They have the sewage system. They control their sewage system. They control their oxygen and their phasing. They control their mixers. They control everything. And the driving there was they wanted to reduce the operation cost, and they also wanted to increase the hydraulic and biological capacity, because this is an area that was in growth. There was a lot of people moving to this area. And the end result is a reduction in the effluent of nitrogen at about 27%. The chemical saving was 46%, and the energy consumption went down with 23%. They had, in their sewage system, they had quite a lot of overflow, but by being able to control the different pump stations, depending on if their retention time, like the retention basins was filling up, or if there was space in the sewage system, they were able to reduce the overflow in that sewage system by 83%, which is a lot. And also the other thing they did was they used the stormwater mode controls module that increased the overall hydraulic capacity of this plant by 80%. Thank you very much. That was all.
Yeah, that's it. Will you read out the question and answer then, or?
Yeah.
Yes. Okay, just making sure you were ready. Yes, absolutely. Thank you so much. I'm going to go ahead and we will start with our Q&A. Very first question, will a certificate be provided for CEUs?
Yes, absolutely. It should follow up with an email and an attachment of the webinar.
Perfect. Thank you. Next, where are the ammonia probes located in the ditch, and what ammonium concentration is typically measured at this location?
Okay, so if we talk about North Cary, or actually any given plant, is that we always place our ammonia nitrate probes in the end of the plant. So basically, if you have a ditch, we will have an ammonia analyzer that would analyze for both ditches, and then we will have, if we want to go light, we'll have one nitrate probe in one of the ditches. Also, in regard to phosphate analyzers, we normally just have one sitting also in the effluent. If we look at the BNR system, we would, and we have we have a pre-anoxic, we have multiple aeration reactors in series that operate in series. We will also place these ammonia analyzers, nitrate probes, and phosphate analyzers in the end there. And when we have them there, we actually able to operate, or to control the DO in all the upstream aeration reactors. We do like an algorithm for each of the reactors, and with that nitrate probe in the end, we also able to use that one for control of the IMLR flow, the internal recirculation flow. We try to minimize the amount of analyzer that is there, because that is definitely one of the big investments when we look at online control. So we try to minimize that as much as possible. If we want to do BioP, we definitely need phosphate analyzer. They're not cheap, and we all know that. But if we don't look at BioP, then of course the phosphate analyzer is not necessary. Yeah.
What amount of the 1.79 mg/LTN is recalcitrant nitrogen?
So
What percentage of the effluent total nitrogen, around that 1.8, and the total nitrogen effluent is recalcitrant?
I don't.
We might have to follow up on that question.
Sure, we will make sure that you do receive
Recalcitrant. I mean, recalcitrant. I mean, so when we look at the 1.979, the ammonia there is basically zero. So we even if we have an online control, we are still fairly conservative with ammonia. If you remember the effluent requirements for ammonia was a 0.5. So, and a TN, we want to meet a TN less than 3, and that requires us to basically remove all the ammonia. The nitrate concentration is somewhere in the range of 0.5 to 1. So and then they do have filters there, of course, as well. So there's practically no TSS coming out of that plant. So the rest is organic, biological, non-degradable TCAN.
Okay. And then we have, how do you prevent hacking of the controls system with a cloud-based control system?
That's a very good question, and not one that I can answer, because I'm not an INT expert in any given way. I do know that we have a lot of security on this one, and what we normally do is that we will have if we have a potential client, and of course this question will come up, that's no doubt about that, then we will have our computer experts having conversations. And so far, when we have had that conversation, it has not been an issue. Before it was cloud-based, we did have like a computer sitting at the plant. The problem was that was a lot more difficult to maintain, and to and what happens also is that I talk about all these modules that you can add and and subtract. And there's constantly improvements or changes on these modules. And so when we have a cloud-based version, it's a lot easier for us to make those changes that is necessary as they are like developed. Also, if a plant want to add modules, it's super easy to do that. And like the plants that we have here in America, we have people in Denmark looking at it. I mean, this is something that can be done all over the world, and can be maintained from all over the world. But we have a high level of security, that's for sure.
Thank you. Thank you, Ashley and Pia, and thank you all. That is all the time that we have for questions today. The contact information for our presenters is there on your screen for follow-up to your questions, and I have collected all of the questions. So I just want to go ahead and turn it back over to you. Thank you.
Great. Thanks everyone for attending, and thank you, WRF, for hosting. Appreciate everybody joining.
Absolutely. Well, this concludes today's webcast. Thank you all for attending. Thank you to our sponsor, Veolia. The recording will be available at wefbuyersguide.wef.org events. We will send all registrants an email tomorrow with the link. Please visit our event calendar to sign up for future webcasts. Thank you.